here, we can maybe get some insight into the evolution of the source region of these Mare volcanic units over time and over lunar geologic history. Just to compare to the Earth, this is a chart of chemical composition of typical mid-ocean ridge basalts, blowing that up a little bit. Comparing the titanium contents from these guys to what we see on the moon, you can see that lunar basalts are strongly enriched in titanium relative to typical mid-ocean ridge basalts by an order of magnitude in some cases. So titanium contents are really unique property of lunar basalts and very important. Traditionally, the way we go about mapping titanium, now I'm not talking about ilmenite here, this is bulk titanium content of the samples, has been using a ratio. Now this is telescopic results here. What they do is they take a ratio of a wavelength in the UV to a wavelength in the visible, and that's what's shown across here, and then they correlate it with the titanium content of the samples. And this is an empirical correlation. It's not based on any particular spectral feature as best we can tell. And it's also not strictly linked to mineralogy as we might like it to be. It's based on a chemical measurement rather than any modal abundance of minerals. And there's good reason for doing that. Measuring modal abundance of minerals in soil samples is very difficult to do. It's much easier to do a sort of a bulk chemistry analysis with fused bead, things like that. But looking at ilmenite in a little bit more sophisticated manner, I'm showing you some spectra that come out of that previous study I was talking about. The purple spectra here are ilmenite separates that we've taken out of one of those samples. And you can see that there's something going on down here in the UV. But if you go out to longer wavelengths, there are pronounced spectral features in the spectra of ilmenite. And with modern remote sensors that cover this wavelength range, this gives us a lot more leverage on detecting and potentially mapping ilmenite across the surface than just relying on this empirical correlation of what's going on down here in the ultraviolet. Some of the effects of ilmenite, so these are pure ilmenites, and then in the gray and black, I'm showing you ilmenite-rich and ilmenite-poor sort of bulk basalt sample spectra. The gray are, so just focus on this dashed line, the gray dashed line. It's a low titanium, ilmenite-poor Mare basalt. It has nice prominent absorption features at 1 and 2 microns, and looks like a typical basalt. And compare that to the black dashed line. It's a very similar sample, except it has abundant ilmenite in it. And you can see that going from this sample spectrum to the black one, the absorption features are much more subtle. You have this continuum slope that's induced, and the thing is, it's overall darker, except for out here as this tail of ilmenite starts to kick in. And so this is a complex system, something we're still working on unraveling, but it provides us a lot more leverage to get at ilmenite content specifically, rather than just titanium content across the moon. So now I'm going to move on and talk about olivine. And I spent a fair amount of my time here around focusing on olivine and the peculiarities of lunar olivine in particular. Olivine is a very useful petrologic indicator. I'm not going to dwell on that. I'm just showing you one example up here of olivine control on liquid composition through its evolution. On the bottom here is the typical reflectance spectrum of olivine. I believe this is the same spectrum I showed you an example of when I talked about MGM deconvolutions. This is San Carlos olivine. It's about 1290, and you can see it has sort of a composite absorption feature near 1 micron that's actually composed of 3 individual absorptions. The 2 on the exterior caused by iron in the M1 site, and the interior one caused by iron in the M2 site. Both of these are an octahedral coordination, iron 2+. And note that olivine is bright and featureless at long wavelengths, beyond about 1500 nanometers or so. Furthermore, olivine reflectance spectra can be used to infer the composition. When I say composition, I mean magnesium to iron content. I'm not talking about nickel or chrome or anything like that. Just major element, magnesium iron. I'm showing you these 3 composite absorption features. This is work that Jessica Sunshine did, and she deconvolved a suite of olivine spectra into these component absorptions, and noticed, well, she wasn't the first to notice this, but she plotted this trend of absorption feature position against composition. You can see that as you increase the iron content of your olivine, the absorption features march to longer wavelengths in pretty regular pattern. There's a little bit of scatter down here, very iron-rich composition, but by and large, these trends can be used to predict the composition of the olivine of interest. you can deconvolve your spectrum into these component absorptions using the modified Gaussian model, for example. But when we look at lunar olivines, they have some complicating factors that need to be discussed. This is an example from the Lunar Rock and Mineral Characterization Consortium back 10 minutes ago that shows an olivine with these small inclusions of chromite. And this is now down here on the next spectrum here, same olivine spectrum from before, but I'm plotting you a chromite spectrum that's reasonably close in composition to some of the chromites that you might find in lunar olivines. And what you can see is that their chromites have these very strong absorptions at long wavelengths. And that really complicates olivine spectroscopy because olivine is very bright and relatively transparent at these wavelengths, but when you introduce this chromite inclusions, it really has prominent effects, which I'll show you on the next slide. So these are 3 examples of lunar olivine reflectance spectra now, and you note that they have still have these same prominent absorption features near 1 micron, but they have these absorption features at long wavelength, which we attribute to these chromite inclusions. And it turns out that these inclusions make it almost impossible to model these guys with a traditional approach that you might use for a terrestrial olivine that doesn't have these inclusions. And so I've had to come up with a modified approach to deal with these guys and return results that are consistent with terrestrial olivines. And the approach that I've come up with is really just to ignore the parts of the spectrum that aren't strictly relevant to my analysis. So that's what I'm showing you down here. I chop off extreme wavelengths and just focus on the 1 micron region. And that produces results that are, for all intents and purposes, consistent with terrestrial results from Jessica Sunshine and previous workers as well. Moving on, now that's all just laboratory spectrum. Moving on, applying this to the moon, so with remote sensing, you have another little wiggle you have to deal with. These are olivine-rich reflecting spectra collected by the Moon Mineralogy Mapper from the Lunar Farside. And you can see that they all have a fairly pronounced continuum slope to them. This is another thing that you have to deal with in a modified Gaussian model deconvolution. You have to supply a continuum slope onto which to superimpose these absorptions. And if you want to have a consistent set of results, you need to have a consistent way to deal with this. So I've spent a fair amount of time wrestling with this and trying to come up with a way to do it. And the way I've come up with is to do continuum removal and to evaluate the effect of that with a suite of laboratory spectra that have continuum slopes basically induced through sort of artificial space weathering. I'm not going to go through the details of that, but basically I've done continuum removal on laboratory spectra to come up with a correction for the continuum slope, effectively. So the results of all of that, that's a big JGR paper that I'm covering in a slide and a half here. The results of that approach are shown here. So I'm showing you the results of the deconvolutions for those spectra that I showed you in the previous slide, now showing their band centers against their predicted composition. And the final corrected compositions are shown in these sort of solid filled blue circles. And they fall sort of right around 70 or so, which is more iron-rich than a typical magnesian sweet rock like the dunites and trochlolites found at Apollo 17. But it's a little bit more iron-rich than you might find in typical Mars salts. But it is consistent with some olivines that are found in feldspathic lunar meteorites, for example, ALHA 81005. And I'm not quoting that these are exact results. There's fairly big error bars when you do MGM deconvolutions, especially with remotely sensed spectra, which have decreased spectral resolution relative to laboratory, and also have more noise. So both of those combine to reduce the accuracy that you're able to get. So in actuality, these should have fairly substantial error bars, but we are in the range of compositions that we see in lunar samples that are consistent with the location from where these spectra are collected. So now moving on to spectroscopic analysis of lunar meteorites. The basic premise of this work is that while the Apollo samples are hugely valuable and have given us countless insights into the way the moon works and has evolved, they come from a fairly restricted region of the moon, which we know from post-Apollo results is actually fairly geochemically anomalous. This is a map of global thorium distribution. Where the high is maybe 13 parts per million. I'm sorry, I don't have the scale bar on here. And the sample return sites are plotted in black symbols here. The Apollo are squares, obviously. And you can see that these are all within the sort of red high region, which has been termed the